Welcome back, everyone. We now proceed to the session 2 of day 6. Now, it's my privilege to introduce our distinguished speaker, Mr. A. Vaidyanathan, Scientist Engineer SG at Satish Dhawan Space Center, ISRO. Sir completed his BE in Electronics and Communication Engineering from Career University, followed by ME in Communication System from Government College of Technology, Coimbatore. He also holds an MBA in Operation Management from IGNOU. He began his career as a senior lecturer in Coimbatore and soon after joined ISRO in 2024. For the past 19 years, he has contributed extensively to India's space missions through his expertise in radar systems, space object tracking, and launch vehicle monitoring. His work involves tracking of space objects for space sit- situational awareness, real time tracking of launch vehicles for range safety, tracking of spent stages during missions, operation, and maintenance of advanced radar subsystems. He has played a key role in the design and realization of radar systems as at SHAR, including India's world-class multi-object tracking radar. For his outstanding contribution, he received the ISRO Young Scientist Award in 2011 and the Team Award in 2015 for, for realizing the active phase array radar. He currently serves as manager MOTR and mobile MOTR operations, SDSC SHAR, deputy project director NETRA project ISRO headquarters. He is also a fellow and a member of several prestigious professional bodies including FIETE, MATMS, ASI, ISSE, and ISNT. We, we are honored to have Mr. Vaidyanathan with us today. So, we warmly welcome you to deliver your session on active phased array radar for space applications. So, the virtual stage is yours.
Thank you, ma'am. Thank you for your introduction. Am I audible?
Yes, sir, you are audible.
Are my screens visible?
Yes, sir, visible.
Yeah. So good afternoon, all. This session is on active phased array radar and its application to space. So I hope this will be a new topic for you. In today's session, I'll be covering on radars and what is a radar and radar subsystem and its application, and what is a phased array basically, and what is a active and a passive phased array, and what are all the applications of the phased array, especially towards space application like tracking radar, meteorological radar, and in remote sensing. And at last, I'll be touching upon some of the radar satellites, imaging satellites, what we have sent, RISAT and NISAT. So coming to this, hope you all know what is a radar. So if you see radar is acronym of radio detection and ranging, and especially the radar technology. This acronym is coined by U.S. Navy as it is used for detecting the objects. Especially it was during the World War time. It could able to detect the aircraft which were coming in a very long range. So as per the acronym, we use the RF signal here to just radiate into space and get the detections from the target. And we used to range the target. Ranging is nothing but finding the location of the target. So that is called as radio detection and ranging. So the technology behind us, you're just sending a signal and getting the reflected echo from the target. And with that reflected echo, you are finding out the information about the target. So if you use RF signal for that, you call it as a radar. And the same technology, if you use it with a light, like a high intense light laser, we call it as a radar, lidar. And same if you use a sound waves, the transverse sound waves, because you know that the targets, especially the atmospheric targets, like the wind at the different layers, so which are so sensitive to the sound, we could able to hear the echoes, right? So if we use a sound for that same, we call it as a SODAR. So here we will be sticking on to the radar. So as I said here, radio waves is being sent towards the target, and the wave goes and hits the target and comes back, and we will be sending a small pulse of signal. So the time taken for the pulse to travel hit the target and to come back to hear the echo. That distance, the time taken, defines as the distance. We call it as a range of the target. So since in this the both ways are involved, the time taken is nothing but twice the range. So we call it as the range is equal to ct by 2, where the c is the velocity of light, and we know that the RF signals travels in the velocity of light. So this is the range, and the direction, azimuth and elevation, what we call it as the direction of the target is taken from the direction at which we are getting the echo. So the azimuth is nothing but the angle measurement from the true north, and the elevation is nothing but the angle measurement from the surface of the earth. So it is nothing but representing the target in a spherical coordinate system. We all know like a polar coordinate system where we have this x, y, z coordinates, and say a point in space can be represented in three coordinates. One is r, theta, and phi, where r is the range, which is nothing but the range in r is the distance from the axis to the point, where is nothing but the range in our case, and theta is from x-axis, so nothing but the direction from the true north, and phi is the tilt from the zenith, or other way it is nothing but the tilt above from the xy axis. We call it as an elevation. And so in any radar which gives a basic these three parameters like range, azimuth, elevation on the target, and if we could able to get the Doppler shift from the transmitted signal to the received signal, and we can also say the velocity at which the target is going, because we all know that a moving target can produce a Doppler shift in the signal which is being emitted or received by the target. So when a radar is capable of sensing the Doppler, we call it as a Doppler radar, which gives the radial velocity of the target. So if you see the applications of radar, there are a lot of applications. We ourselves may not know. There are even a small radar has come into picture now. Even our new cars have got a radar in it, which can proximity sensors, what we say, which can sense the object nearby. So the auto-guided vehicles have come with a small radars. But if you see the history, the major applications of radars are like radars were primarily used for tracking, what we call it as a tracking radar, or the second thing is like surveillance. So it keeps on doing the surveillance, and if any target is going in that vicinity, it detects and it tells us. And third thing is like it is used for meteorological application. All the Doppler weather radars on the coast, what IMD, they just keeps on track the cloud around them to tell that what is the intensity of the cloud and what is the probability of rain. So that we call it as a meteorological radar. And other thing is like all the ships which has a radar to to guide itself into the deep sea, and especially when it comes or approaches, when it comes to the deck, the shore, it has a radar in it, which is called, we call it as a navigation radar. And we also have radar in the satellites, what we call it as a radar imaging satellites. Apart from the optical satellites, the satellite has a radar which has got an advantage, which we will be covering in the subsequent slides. And also the radars are used in interplanetary missions. Whenever our Chandrayaan 2, when it 2 and 3, when it went, it had an onboard radar to especially to find out the location where it needs to land. And apart from that, it is also used in space vehicle, like space shuttle has a small radar, which is used to precisely dock it with ISS. And also the radio astronomy, also radar is being used. These are the overall applications of radar. Coming into the major subsystems of radar, radar basically has a huge transmitter which generates the RF signal, required RF signals of huge power that is being radiated towards the target through the antenna. And the signal, either it can be a pulsed or a CW signal, continuous signal. It goes, hits the targets and comes back. And the received signal is again received by the same antenna, and it has been sent with a duplexer, it has been sent to the receiver. And this receiver detects the signal, and above its noise floor level, it detects the real echo from the noise, and it gives to a system where this range system has the mark of where the transmitted signal was and where the echo has come, which tells us the range of the target. And this antenna is oriented towards the target with the drive system, and from the received echo, the errors, required errors to follow the targets are generated, which is given as an input to the servo system so that the antenna keeps on following the target. So that orientation of the antenna gives the orientation of the target. So with that, the required range, azimuth, and elevation of the target are arrived. So in real time, it becomes a closed loop. When a target is being locked, the antenna and the other systems work together to continuously follow the target to get the target information in real time. So this is the overall block diagram of any radar system. But based on the application, as we have seen, the target differs. Like, if it is a meteorological radar, that radar also works in the same principle. But whereas the target there is, instead of a launch vehicle, will be a cloud, or say the atmospheric stratus. So it tries to get the reflection from the atmospheric stratus and tracks it. So especially in a launch base, a high precision tracking radars act as an independent source to provide the exact position of the launch vehicle to know to whether the launch vehicle is going in a right path or not. And that input is very vital for the range safety officer to allow the launch vehicle to follow its path. And as I said, for all these two things to happen, the main thing is the transmitter, which generates the huge RF power, required RF power. For example, a radar of such these things of this level has to generate a power of 1 megawatt for a small duration of 1 microsecond. So such a huge power transmitter is required. So what we use is we use a cross field devices like magnetron, which generates a huge power. So this was the conventional magnetron, but right now the current trend is the huge cross field devices which generates the huge power are being replaced with the solid state devices, where we use this IGBT or GaN based or gallium arsenic based power amplifiers, and we have a huge small power amplifiers, and we have a couple of more number of power amplifiers put together operates, and when we combine the power, we get the required power. The advantage of this solid state is, like, here it is not a single element. So when a single amplifier fails, the complete system will not be down. So in magnetron, if anything fails, the complete transmitter will be down, and the radar cannot track. But here, since it is a group of power amplifiers, even if one amplifier fails, with graceful degradation, the radar can track, and the system will be available. And there are a lot of advantages when we go towards a solid state, when we are moving towards the phased array technology. The solid state transmitters play a very vital role. And one more thing also, we call it as a pulse compression technique, which I was telling you, right? See, when we are using a magnetron, if we require a 1 megawatt power, the magnetron generates that 1 megawatt power with a very short pulse within 1 microsecond. Within 1 microsecond, a 1 megawatt RF power is being generated. So effectively, an energy of 1 joule is generated. This peak power is required to find to detect the target at a very long range. But whereas the solid state amplifiers cannot generate such a huge power. So what you by a single device. So what you do is we use a more number of small devices. For example, we use, if we are using a 1 kilowatt amplifier, we use say 100 such 1 kilowatt amplifiers put together to generate 1 megawatt of power. But one advantage over that is, like, see, the heat dissipation is not at one point, at multiple point, so that we can take care of, so that the noise generated by the system will be more effective. And coming to other thing is, like in pulse compression technique, instead of generating a huge single pulse with a huge power, now the technology towards is, like, you generate a wide pulse with a low average power. For example, you can generate a 1 kilowatts of power, but with, instead of 1 microsecond, you radiate for 1 millisecond, so that the effective power is again 1 joule. But the difference here is, see, if the transmitted pulse is 1 microsecond, 1 millisecond, and the received echo will also be 1 millisecond. So what happens is, for a radar to be more accurate, the narrower the pulse, the more accurate will be our detections. So here what happens is, if the pulse is becoming wider, our resolution become poorer and poorer. For example, if this 1 microsecond is 150-meter resolution, if you see CT by 2, if the RF energy goes in velocity of light, 1 microsecond corresponds to 150 meter, but whereas here it becomes 15 kilometers. Our resolution is 15 kilometers. So unless or otherwise two targets are not separated beyond 15 kilometers, we cannot identify it as a two targets. But the good part here is in a pulse compression technique, a new technology where while transmission, we transmit a wide pulse with say low power, but after receiving, you compress this pulse to get a narrower pulse so that the range resolution is also met. So that is called as pulse compression technique. So here not all the signals can be made like that. If a signal with a known phase information is being transmitted or a chirp, in an analog we call it as a chirp with a required bandwidth. If we transmit a wider chirp signal, after receiving it, we can de-chirp to form it as a narrow signal so that the transmitter will be radiating only a less average power, but whereas the receiver after compressing will be seeing an echo equivalent to a peak power and narrower pulse being transmitted. So these things can be easily implemented with a solid state devices. So that is the important thing which is making the radars and other system to go beyond the range capability. And coming to how a beam is formed in space, we all know that a radar, if it has a parabolic reflector, see, for example, if this is a radar with a parabolic reflector and we have a say source which is at its focus, and if that signal is being radiated towards the parabolic reflector, the signal which is hitting all the surface of the parabolic reflector are reflected as a straight parallel wavefront. When so this is the principle of parabola, right? When a signal is being transmitted from the focus, it tries to reflect all the signal parallelly. So if you see in this wavefront, all the signals will be of equal phase. So what happens is when all the signals are in equal phase, when it travels together, it combines to form a beam in this direction. In this direction. So this is the concept at which the collimation happens and a beam is being generated from a parabolic dish. So the dish is constructed in such a way. So the radiating horn will be in the focus of the dish, and this FYD ratio is maintained, and this diameter of the dish dictates the beam width of what is our required beam width. But here this is the conventional antenna we have, parabolic dish. But what happens is if you want to move the beam, we need to move the entire antenna. So a mechanical drive systems will be attached to this, and when we excite the drive system, the antenna moves so that the beam will be moved towards the required direction. But the coming to the new thing like phased array, here instead of see generating, what we want is a one pencil beam in the direction, in the required direction. But instead of having that pencil beam with a huge huge mechanical dish, we go with a group of small antennas which are working together, and each antenna will be radiating individual signals. And what happens is if all these signals are in phase, and when these are traveling towards each other, the as I said here also in this direction of, we call it as a bore site, in this direction all the signal will be having the same phase, so that all these signals sums up to form a beam in this direction. But whereas in all other direction, since they are in out of phase, they die down, and whereas the maximum energy will not be there in that direction, all the maximum energy will be towards the direction of the bore site. So this is what the beam is synthesized in the space using the phased array. But here, one of the main advantage over here is, like if we go for a phased array, suppose if we want to steer the beam, here as we are moving the antenna, here we no need to steer the antenna. You just introduce a progressive phase shift between these elements. So when they are traveling, this progressive force shift will tilt the wavefront. So the maximum what we are seeing in this direction will be seen in this direction. So the beam starts forming in other direction. So that is how a beam can be steered without moving an antenna, which is a major advantage of the phased array. So here, I think this will easily explain you. So if we have one isometric antenna, so it will have one beam. But whereas if you combine the more number of antenna, when see, this is the antenna pattern. One element will have a very wide antenna pattern. Here even the beam width is very wider. And if you combine more number of antennas, here these antennas are spaced with equidistance between them. So what happens is the combined antenna effect creates the beam narrower. More the number of antenna is being combined, the beam becomes narrower and narrower and narrower. So here if you see in this, say for example 6 antennas are being combined, so the effective beam width what we are seeing here will be 6 times lesser than the beam width of one element isotropic element what we have seen. But in this condition, if you could able to put a phase shifter between each elements, and if we could incrementally give a known phase relationship, induce a phase between each and every radiating element, then that will shift the wavefront as we have seen in the earlier slide. That will shift the wavefront here, so resulting in the maximum energy getting converged in other direction, so which will result in the beam getting moved. So if we have a phase shift, we have the capability of moving the beam, what we call it as a beam steering. So as the antenna aperture increases, the beam width decreases, and hence the resolution increases. So radar range, if the narrower the beam, the target's range resolution will be very good. And as the number of element increases, the antenna gain also increases. So if you see the types of array, there are many types. One is a linear array, what we have seen. Linear array is, say, a number of elements kept in a line with a known distance, equidistance between them. So that we call it as a linear array. And in that linear array, it is nothing but a one-dimensional array. If you give the phase difference between the elements, then towards that, as we have seen earlier, the beam can move from left to right. So the beam movement will be there in only in one direction. Suppose if I could construct an array of linear arrays. So for example, this is what we call it as a planar array. An array of linear arrays, if you could able to make, then I have the now I have the capacity to introduce phase difference in both the axes. So in x-axis, if I make it, the antenna will be moving from left to right. And if I could able to give a phase shift, progressive phase shift along x-axis now, earlier case is y-axis, and y-axis now, x-axis now, then the beam will be moving from front to back. So with a planar array, I get the beam movement in both the direction. So what we call it as an azimuth and elevation. So mostly all the antennas what we are using in radar will be a planar array, so which has both the azimuth and elevation movement. And the next thing what we use, what we say is a conformal array. That is nothing but the antenna on the surface of any curved surface or on the body. For example, if you see a flight air jet, the nose cone, on the surface of the nose cone, we have an array. It is nothing but the planar array sitting on the surface of this. So here what happens is we take care of the surface curvature also in computing the phase difference between the elements. So this gives a very wide angle steering. And here but one disadvantage here is it is very complex, where in planar array, based on the distance, the required phase difference can be easily computed. But in this case, the phase difference due to the curvature also properly has to be accounted to get a beam in the required direction. So these are the different types of phased array, and mostly in a ground-based systems has a planar array, and the airborne system like flights and aircrafts, launch vehicle has a conformal array, and that conformal is will be based on its surface of the particular launch vehicle or aircraft. So this is what we were seeing. If the number of, so here, if we have an array of n elements which are spaced in a distance of d, then the total length, total size of the antenna will be n into d. So that will be the total length. And when d is the inter-element spacing, when each element is placed with a distance of lambda by 2. So what happens is, if the n varies, that means the size of the array becomes more and more and more. So if that is the case, when n varies, the length or the size of the antenna becomes more, then obviously the gain of the antenna improves. So if you could able to see, when the size of the antenna becomes more and more, the beam width becomes narrow and narrower, and the gain improves. So here you could able to see compared to a 9 element array, 18 element array, 27 element array, the 27 element array has a narrower beam width and a higher gain. Similarly, if the D increases, but in this case, if the D increases, then also the length of the array will increase, but whereas the number of elements is fixed. So in this case, what happens is if the D increases, the gain remains constant because the number of elements which is being radiating remains constant. So the gain of the antenna becomes constant, but whereas the inter-element spacing increases, so which will which will result in a grating lobe. So what happens is, see, if 1 minute. So in the previous case itself, if you see the number of elements, even if it is say the inter-element spacing of 1 minute lambda, okay, inter-element of spacing is lambda. In this case, so lambda it is more 1.5 the lambda, and if it is 1 lambda by 2, so here the effective antenna size is becoming more, so the beam width is becoming narrow, but the gain is not improving, gain is remaining the same. But the thing is, if you see the wider spectrum like this, probably here you can see it will end up in a grating lobe. So if you see, if the inter-element spacing is lambda, there is no grating lobe. But whereas when the inter-element spacing increases, if it is more than lambda, then the grating lobe starts coming. So which means that we cannot steer the beam beyond this. So if we are radiating in this direction, even any target in this direction's echo also sums up. So we cannot differentiate between the targets from this direction to this direction. So for any radar which is operating the phased array, which is operating in a concept of phased array, it will take only, it will have the beam steering capability limited only to the space where there is no grating lobe. So if you see in earlier case, when the lambda is 0.5, in that case we have a beam steering capability of -80 to +80, but whereas if the lambda is 1.5 lambda, then our beam steering capability reduces to only -40 to +40. So which is very much important for a radar. The steering capability is very much important for a radar to track the target. So that's what, when it moves off, the grating lobe increases. And also you could see that when the beam starts moving from the its bore side, its gain reduces, but whereas the beam width broadens. So these are the principles of phased array. But one thing is, like, for a tracking, any tracking radar, the target is always will be tracked only in the main beam. So we should be so cautious that there should not be any grating lobe, and the side lobes should also be as low as possible. In some case, if the side lobes are say shorter, less than only by only say 7 dB or 8 dB, then any strong weak target may be in the main lobe. Our intention is to track the weak target. But whereas when a strong target comes into the side lobe, which is say in RCS 20 to 30 dB more, then the side lobe will give you more signal than a weak target in the main lobe. So towards that, to properly differentiate the target, the main criteria is the side lobe should be as low as possible, and there should not be any grating lobe. So the main advantage of this phased array is, like, we can do beam shaping. We can alter our own side lobes. These things are not possible with the mechanical antenna. So here, like, even all the when n elements are excited uniformly, then we have a beam like this, which we call it as a normal beam, with the first side lobe levels at 13 dB down, and all the other lobes are dying down. But whereas if you could able to apply some, say, pattern of excitation for our elements, so here it is a uniform excitation, or n elements are excited uniformly. But if I use some windowing function in exciting, for example, I can use a triangular function, I can use a Hamming window, or I can use a Hanning window. So those are the series, regular series available. By using that, we could able to suppress the side lobe levels. So these are very well known available series. Even Taylor series also is possible, where the Taylor series is the most well used, where you can define your own side lobe level, what it is required. But apart from other things which has a more or less like a fixed side lobe level truncation. If you see the triangular side, if you apply a triangular series, it has a first side lobe level as minus 27. Hanning series can bring the first side lobe to minus 31 dB down. The best thing is the Hanning window, which can take up to minus 58 dB down. But such thing can be made at the cost of, see, while you're reducing the side lobe level, the main lobe level broadens. So our the narrower beam with what we were expecting slightly broadens. So the power which you are trying to suppress in the side lobe gets pushed into the main lobe and cause the main lobes to broaden. So towards that, what happens is it reduces the, by reducing the side lobe, the beam width broadens and also gain slightly reduces. So it is a trade-off. So trade-off between the gain beam width to the side lobe level. So this should be taken care while designing the antenna. But this has the phased array has this advantage. So we can shape the beam in whatever way we want. So this is what I was telling you. Like in a phased array, whenever we are exciting all the elements with a uniform phase, then the maximum power combining happens at the bore side, and all other direction the signal dies down. But whereas if we excite each and every element with a known phase, for example, in this case, each element is given with a known phase of say incremental phase of delta t, which results in the bore side, the signal to get shifted, because in that direction the wavefront, all these wavefront is shifted in this direction. Earlier it was parallel, this all the wavefronts is get it shifted, so towards that direction the beam starts forming. So that what we call it as a electronically, by varying the phase shift, the beam gets shifted to the required direction. So here the advantage is, we can adaptively switch the beam from one direction to the other direction, and also you can shape the beam in whatever way you want. What we seen earlier, by using the tapering and other things, like you can shape the beam in whatever way you want. We call it as a pencil beam, very narrower beam, where all the maximum energy radiated by the transmitter is put towards one particular beam, very narrower beam. So a pencil beam is always preferred by a tracking radar to track with a high resolution. And second thing is adaptive beam, based on the target thing, you can adaptively in between they split to form two beams, or you can just have multiple beams simultaneously, especially in surveillance radars have multiple beams, so that when a target is going fastly crossing you, any one of the beam hits it, and you can say where the target was. Or if it is crossing you, it starts moving from one beam to other beam, it tells you the direction at which the target has moved. And also multiple pencil beams simultaneously. This is like to track multiple targets simultaneously with multiple beams. So such an adaptivity we will have when we go for a phased array. And also you can even shape your antenna pattern. Suppose you feel like there is a jammer sitting in a particular direction in a var field, then you can alter your pattern in such a way that, see, you can alter your pattern in such a way that in this particular direction my pattern should be 0, so that whenever the beam starts radiating in that direction, that in that direction the pattern will be 0, so you will not be radiating towards it. Or else if the jammer, a particular signal is constantly coming from the direction to jam you, you will avoid receiving that signal. So such advantages are there with the phased array system, where the main advantages compared to a mechanical parabolic dish which we saw were, in phased array system we can make beam shaping, we can do by ourselves. Then adaptive beam forming, in real time you can just change the shape of the beam whatever you want. And beam agility, what we say is, like, beam at a given spot of time can be switched from one direction to other direction. For example, if you are having a mechanical dish here, if the beam needs to, from here it needs to go here, mechanically the antenna needs to travel from this direction to this direction. But here it is not so. If you are seeing the beam here, the next instant the beam can be seen here. So we call it as a high speed switching of electronic beams. So we call it as the beam is more agile in this case. And next thing is, it is highly reliable, because it is multiple elements, even one or two elements fail, also the system is available. And this particular phased array is more advantageous in a huge system, like especially in defense system like this, where we have multiple mode of operation, like search, track while scan. For those things and all, electronically the beam can be taken to any direction we want. So the phased array antenna is very important towards that. So here is just, I have just listed down the difference between the mechanical and electronic beam steering. The mechanically controlled beam, it's a single aperture, mostly a parabolic dish, whereas in phased array, it can be either a linear array or a rectangular array or a conformal array. A beam is moved by moving the antenna mechanically, but in this case, beam is switched to required direction instantaneously by what we call it as electronic beam steering by applying the required phase shift. Here, the mechanical lag prevents to see the targets in different directions simultaneously. But whereas here, since we have the switching, we can fastly switch between two directions so that the targets at two directions can be simultaneously seen. And the objects in an actual field of view given by the mechanical direction of the parabolic reflector alone is used as a detection. But whereas in the object in different direction can be detected and measured electronically. And the advantages over here is, okay, a continuous surveillance radar uses mechanical disk can be used, and precision tracking radar. If you want to track only one single object very precisely, in that case, say a mechanical antenna still has its advantage. But whereas a scenario where you want to do multiple operations like search, track while scan, tracking multiple targets simultaneously, high resolution imaging, in those applications and all, compared to mechanical dish, the electronically controlled phased array antenna has a very big advantage. And coming to the phased array, there are two things. We call it as an active phased array or a passive phased array. The active, see, it's basically an array antenna. If all the elements in an array are individually controlled by a TR module, then we call it as an active phased array, because the beam can be agilely switched to any direction by controlling the phase shift of each and every element. But whereas if the group of element is controlled by only one particular transmitter and receiver, then we call it as a passive array. So in this case, what happens is a huge, again, this system has a huge transmitter, as we said earlier, and that power is being split among these elements, and these elements has a high power phase shifters for steering the beam. So as of now, the technology is moving towards active phased array, where the beam is very agile, and also the each and every module has its own transmitter and receiver. So in this case, even if few modules fail, also the system is available. But in this case, even if the exciter or the receiver systems are single system, if one fails, even the radar is down. So now the technology is towards active phased array, completely active phased array systems. So again, I have just given the difference between the active phased array and passive phased array. This anyway, I have told the same things here. But major thing is, like in active phased array, the gain of the system will be more. And just 1 minute, 1 minute. Just I'm getting a call. Just 1 minute. I'll be coming. Am I audible? Am I audible?
Yeah, you're audible.
Yeah, yeah. Please. Sorry for the inconvenience.
Yes,
Just
sir.
I'm getting all this will continue. Okay, so we were just discussing about active and passive phased array. The main thing is like the gain and the efficiency of the active phased array is more compared to the passive phased array, and the reliability wise, here the systems are available. It has a graceful degradation, whereas the passive phased array has a single point failure. If the transmit or the receive system is down, it will be completely down. And coming to the radars, which the ISR, especially the in ISRO, the phased array systems, which are all available, is one such as a multi-object tracking radar, which is an complete active phased array radar, which has been indigenously designed by ISRO, and which has been operational from 2015 onwards. So it is an active phased array which works in L band, 1.3 to 1.4 gigahertz. It is primarily meant for tracking a 0.25 meter square target up to a range of 1,000 kilometers. So it has an array, a planar array of 11 meter cross 5.7 meters, with 4,608 independent radiating element, and all these elements are completely active. So that means each and every element has a 200 watts a TR module, and the TR module is capable of radiating 200 watts power, and it has a LNA which is of about 30 to 35 dB gain. So it being completely active, the beam can be easily switched between the targets. So that the multiple targets tracking, as per the name, the multiple targets can be tracked simultaneously. So the main objective of this particular radar to design was to track multiple targets simultaneously during the mission, and also for during other scenarios. And as I was telling you, the pulse compression, linear LFM based pulse compression is being done, where the compression ratio of 8,000 is being achieved. A 39 dB pulse compression gain is achieved, which is very much important to track a long range target in a skin mode. So this radar is capable of operating in search, track while scan, and dedicated track. And the principle behind tracking multiple target is, here only one single agile beam is used to track multiple target on a time shared basis. Earlier we were seeing, like beam shaping, where the beam can be split into two to track. So such things will work when the targets are nearby. But whereas, if you want to see a targets which are all of long range, if I just split the antenna into the beam into two, what happens is the power radiated in each the beams comes down, and the beam width also widens, so that you cannot see the targets in a long range. Suppose the targets in long range are as concerned, so we use again a single pencil beam and use a time shared basis. We hop between the target to track the multiple targets simultaneously. So this particular radar is capable of tracking 10 simultaneous targets, all at the range of 1,000 kilometers at 1 hertz rate. And it is completely adaptable, being completely designed in India. It is completely adaptable. It can operate from various variable pulse width from 10 microseconds to 2 milliseconds, and a variable pulse repetition frequency of 50 hertz to 200 hertz. So like if all the targets are at closer range, it can go for higher rates, or if it is a longer range, it tracks the targets with lower rate. So it is completely adaptable. So as I told you, the main thing for designing this particular radar was, like, about any launch vehicle profile. You will be just seeing it like any PSLV or GSLV rockets when it is being launched. Rocket is not only a single target. It is a combination of multiple stages. Like if you talk about PSLV, it is a combination of 4 stages, like solid stage, liquid stage, and again a solid state, and final is again a liquid stage. So each and every stage, once its work is over, it separates. Even if PSLE, if you see, along with the first solid stage of say S139 ton core motor, again 6 numbers of say solid strap-ons are there to increase the thrust further. So what happens is, once those things are burnt, they separate. So if you see a typical PSLV profile will be like this. So once it is lifted on, the groundlet strap on. What I told us, like lift on happens when the first stage fires up, and once it is fired up, to give additional, along with it, 4 strap-ons fires up, and that we call it as a groundlet strap-on firing. And after a few seconds, to increase the thrust, the airlet strap-on again fires. So once these things are over, the one which the groundlet strap-on fired along with the core motor stops, that separates. Now after 20 seconds, the airlet strap-on separates. Then once after say 120 seconds, once the first stage completely burns out, here the first stage gets separated. So once the first stage gets separated and the second stage fires and is a liquid stage, which again burns for 120 seconds. So I mean, in the due course of the second stage, once the launch vehicle would have by that time attained an altitude of more than say 70 to 80 kilometers. So at that time, what happens is we are away from say 100 kilometers. We are away from the atmosphere. So what happens is the heat shield, which was protecting the satellite up to then, opens up. So we call it as a say the first stage and the heat shield, the payload firing separation. And once the second stage is over, the second stage separates, and then the third stage ignites. The third stage is again a solid stage which burns for say a couple of 100 seconds. And once the third stage is over, the final say before firing up the final stage, the vehicle goes into coasting for some time, and the final stage, once it fires up, it takes the satellite to the required orbit. So the main purpose of each mission is you have a satellite of a particular payload and you want to put that particular payload into a required orbit. For example, PSLV is polar orbit. So polar satellite, somewhere around 600 to 800 kilometer polar orbit. So if it is a GSLV, geo transfer orbit. So that is nothing but say 175 kilometers to 36,000 kilometer a geo transfer orbit. But you have a mass of a satellite. So a 1 ton mass, say 2 ton mass satellite or a 4 ton mass satellite needs to be put into that orbit. So correspondingly, the launch vehicle guides and takes the satellite to a particular height. And once the particular velocity is achieved, we say that the injection parameters, the required velocity for the satellite is achieved. Now we can release the satellite. So what we call it as a satellite separation. So that decision is taken by the final stage on its own. Once the particular velocity is achieved, the satellite is put into the orbit. So here if you see, there are multiple stages, and each and every stage, once it is over, that particular stage is taken, once it is separated, that falls into the atmosphere. Okay, because that once its velocity, the thrusting velocity has gone down, it falls into the atmosphere. But the only thing which goes into the orbit is the final stage, because that also has got its own velocity by that time. So once it is separated, once the satellite is separated, the final stage will be in orbit. The work of the final stage is over. So what we do is, with the left out fuel, we just passivate it. We call it as we left out that particular fuel, and that stage, all the pressured gas, pressurization, all those things are released. And from then on, that particular stage as a dead mass, it will be in the orbit. So that we call it as a rocket body. So any mission, if you see, what are all the number of useful payloads it is carrying? It may be one satellite, two satellite, three satellites. Those satellites will be put into a required orbit, and at last the final rocket body as a dead mass will be in the space. So if you see, during the stage of say a launch vehicle, uh, uh, the launch vehicle also carries a transponder with it. So all the single object tracking radar gets locked to the launch vehicle using the transponder. Transponder is nothing but a beacon. Like if you send a signal, that launch vehicle will send back one more signal, so that you can track up to the range possible. But if you track in skin mode, primary mode, by radar's conventional principle, like radiate your signal and get back your own echo and track. So that will be limited to a particular range based on your, because you are sending a signal that goes, hits and comes back. The echo will be very weak. So you cannot track more than that. So that's what the radar which are used for range safety tracks the target with a beacon present in the launch vehicle. So once the radar echo hits the target, the onboard launch vehicle sends a strong signal back. So the beacon sends a strong signal back, so that the radar receives and tracks for a long duration. So here what happens is, we wanted a radar which could able to track multiple targets. What are all the stages getting separated, that also needs to be tracked, because when we were working towards the reusable launch vehicle technology, like now the SpaceX was doing, we had this some 10 years back, where not 10 years, 15 years back, when we wanted to just also track the separated targets and see where it has spent down, we need to take it back and use it for the next mission. So that we call it as a reusable launch vehicle. So what happens, you should have seen that RLVTD, which is getting launched as a rocket, which goes along with it, and after going to orbit, it comes down and lands as an airplane. So that you would have seen a couple of our landing experiments which were happening. So those things and all, when we are using it, so multiple targets will be there in the scenario. We need to track all. So one radar capable of tracking multiple scenarios is required. So when we are tracking multiple targets, I cannot say that I can track only with the help of a beacon or a transponder. So the radar should independently track even the forward moving and also the separated targets. So a long range skin mode tracking is required. So this radar was designed for it, and you could able to see a theoretical profile at the left side and a real profile after tracking. You could see that once the first stage was separated, that is being tracked along with the forward moving. Then along with that, the heat shield was tracked, and the second stage was tracked, and the third stage still going on. And you could see that by this time our elevation is 0. So we have lost because the target has gone beyond the curvature of the earth. So a single radar can track all the targets and give you the real picture. This could happen only because of the phased array technology, where the electronically the beam could able to hop between these targets and give the echoes. And in background there was a good computer which could able to associate the targets returns coming from each target, give it to the corresponding target and track it, so that the all the tracks can be could be maintained during real time. So this is the one of the main advantage of having a phased array radar, long range phased array tracking radar. And as I was telling you, this particular radar is also used for tracking the space debris. I was telling you the final stage after putting the satellite goes into the orbit, right, as a dead body. That dead body is called as a debris. So here, if you see, generally what is a space debris is, space debris refers to material that is in an orbit as a result of our space initiative, but it no longer serves any useful information. That means, see, we are sending a satellite to an orbit of 600 kilometers. So it is there in an orbit of 600 kilometers, and it is doing its work. It is generating the power from the solar energy. And say if it is a remote sensing satellite, on a daily basis, it is taking picture and it is sending us. But what happens is when it is rotating the Earth with respect to its gravity, gradually its orbit comes down. So what we do is on a periodical basis, say once in a month or once in 45 days, we just see the altitude and we slightly the fire it and take it to its original altitude. So the satellite has got an propulsion system in it. So by firing its propulsion system, we take it to the required orbit. So then it continues working in that. So that we call it as a station keeping. So what happens is, so there is a propellant already loaded into the satellite. So with that propellant, I can say that for 10 years, I can do station keeping for this satellite. So the required energy, electrical energy, is being generated through the sun. But whereas for firing the thrusters, the fuel is taken from here. So what happens is when this fuel is over, then what happens is, even though if the satellite is drifting, we cannot fire and take it to the required orbit. So once it is not in the required orbit, then it will not do the intended job. Say for example, if you have put a remote sensing satellite, and that remote sensing satellite is the lenses and cameras are designed to work at a particular altitude, and if it comes down, then the image quality will not be same of that. So what happens is, we say a satellite is live unless or otherwise till up to what time we could able to housekeep that particular satellite. So if we know that the fuel is becoming depleted, it is going to do, then we say that the satellite has come to the end of life. And from then on, for example, if the 10 years is over, the end of the life is over, we say that that satellite is dead or it has done its job. We immediately plan for sending one more satellite. But what happened to that particular satellite? The satellite which we have declared dead will not come down, right? It will be there in the space, it will be revolving, it will be rotating, but uncontrolled way. We cannot control it, so it goes into uncontrolled way. So there are a lot of such objects like which after the end of life, which is revolving as a rotating as a dead object, what we call it as a space debris. Like even after the mission, once the mission is over, after putting the satellite into its orbit, in the final stage of the rocket, after depleting its fuel or passivation, from the next day onwards, it's a debris. So likewise, if you see the out of all the space missions, out of all the things, the if you consider about the active satellites which are in use, if you see, there are only some 5,500 to 6,000 live satellites are there. But whereas if you see the total space objects in space, there are nearly 35,000 space objects are there, which are a resultant of earlier missions. So if you see it, compared to all the objects in space, only 1 in 7%, 1 in 7, 1 by 7th of the object is an active satellites which we are using it. Remaining thing are debris. So these debris are uncontrollable. They rotate freely. We cannot control it because electronics is off. And what happens is this may come into live contact with any of the live satellites, and they themselves two debris may collide. Once they both are all are rotating at 7 to 8 kilometers per second. So in a 7 to 8 kilometers per second, if two things collide, that creates a hypervelocity collision where it totally, whatever may be the size, they disintegrate into thousands of pieces. Okay, such things should not happen. So what we call it as like a space-based collision. One such thing has already happened one fine day when in somewhere around 2005 or 6, yeah, Iridium 33 and Cosmos 2251 satellites. One was a live satellite in it, and one was a debris. Got collided, and one fine day there are nearly 2,000 debris were formed, and both the satellites were lost. So we should not, such things should not happen. So what we should do is, even all the debris, all the live satellites are being tracked by the ground stations. So we know the positions of the ground station, live satellites. Each and every day on a round-the-clock basis, the satellites are being tracked and the informations are updated. But whereas the debris like this are tracked by the radars like MOTR, which there are a couple of radars all over the globe by all the space nations. They on a constant basis they track these debris and they update their parameters on regular basis. So these cannot be controlled, but their positions are regularly updated so that the live satellites, if they come into contact with it, they can they deviate they can maneuver the live satellite to get it protected. So for that, even the tracking the space debris is also very much important. So this MOTR, apart from the launch day, it regularly tracks space debris. So whenever any objects it comes above us, it tracks it. So we could have only a particular, see, if it is in an orbit is around the globe, but we cannot see completely. But you will be seeing only when it is above us. So this orbit, a small track with that data, we process the data to settle in which orbit the particular debris is. So on that basis, on a daily basis, nearly some 30 to 35 debris are being tracked on a regular basis to have, and mostly all our own debris, Indian debris, are tracked on a regular basis and updated. So this is a very serious concern. If you have some accidents on the space, a mission will be lost. A particular satellite, if you see a particular satellite is lost, what are all the services rendered by the satellite will be lost. So we should not afford to such things in space. So it is taken as a serious concern, and it's a threat to all other people also. Whomsoever may be the satellite in the space, it's a threat to them. So on a serious note, this has been seen, and radars like this are regularly monitor those space debris, and they give alert to a particular person whose satellite, whomsoever may be, whom satellite has a threat. They alert them to maneuver them. So these are the applications of tracking radar. Now coming to meteorological radar, the phased arrays are being used in a meteorological radar. As I said, one such thing is a wind profiler radar. So it is an active array radar which is operating in say 48 to 52 megahertz frequency. Especially this 48 to 52 megahertz is in the VHF band, has a very good reflectivity to the atmospheric stratus. You may know what is a strata. The atmospheric layer, if you see, we say is from troposphere, mesosphere, stratosphere, ionosphere, exosphere, right? So each and every layer of atmosphere has a different densities. So, and also the velocity of the wind at the bottom layer, troposphere will be more, but when you go up and up, the temperature and its the humidity content will be different. So correspondingly, there the temperature will be different. The ionic content will be different. So which will see that the different reflections will be coming from different atmosphere. So here, so we need to study what is the velocity of the wind at the different layers. I was telling you, right, especially up to 60 to 70 kilometers, there will be atmosphere, huge atmosphere will be there. Beyond 100 kilometers, there will not be that much, more or less, like we call it as into space. The into space is mostly beyond 100 kilometers. So we have all this wind and all other things only below 40 kilometers more. So this launch vehicle, once it is lifting up, it should seamlessly cross this 40 to 50 kilometers, where this wind, even all this like cyclonic effect, all this say monsoon, rain, cloud, those things will be there, right? So it has to cross all these things and it has to go. So towards that, when a launch is going on, the launch pad, the launch base, and the area surrounding to the launch base, where especially the launch vehicle travels, these areas are regularly monitored by our meteorological team for any rain activity or cyclonic activity, thunder activity, or any, because even lightning is very dangerous. If a lightning hits an launch vehicle, all the electronics will misbehave. So such activity, and so these things will be continuously monitored by the meteorological team with the help of some radars. They use wind profiler radar to see the wind velocity movement vertically from the launch base, because once the rocket launch lifts off, it has to clear all these velocity and go. This, if the wind is more, and that should not be an obstruction to the launch vehicle. See, what happens is, if the launch vehicle is lifted up, it will be going up with its thrust, but this wind, head and wind, can hit the launch vehicle and try to turn the direction of the launch vehicle. So then such things should not happen. So for that, there is one thing called as DOLWB, day of launch wind biasing. So compared to 15 days before, on a launch time, they will study the wind pattern, how it is, and with that, the information is given to into the launch vehicle at t minus 20 minutes. They feed so that the launch vehicle has the information up to 40 kilometers when it is traveling, where the wind, head and winds are expected to what level. So correspondingly, the rocket thrusts itself to avoid the head and wind load of the head and wind load. So that we call it as a wind profiler radar. So wind profiler radar, since it is a VHF, the antenna size is bigger, and even at a zero point 0.7 lambda, the size of this particular radar is 300 meters wide. 300 meters wide, 576 elements. So this continuously takes the echoes from the atmosphere, and on up to 21 kilometers, it gives a wind profile. So it works round the clock, and every 15 minutes, one profile is being taken. So this is very much important for a ground-based, say, spaceport like Sriharikota, where the rocket launch is expected in throughout the year at any time. So that has been done, and this is one of a very good example of a phased array system. So you can see that a single pencil beam is being generated, and that swings in northeast and east west direction to see the Doppler, to give the meridional wind and zonal wind. One minute. Yeah. So, and there is also one more facility which is near our Tirupati Gadanki. And apart from contributing towards the launch wind profile, they also regularly do the MST studies, what is called as atmospheric studies. That we call it as a dedicated National Atmospheric Research Laboratory, NAR, we call it as, where along with the other institutions and universities, people regularly do a space research activity, where the up to ionosphere, troposphere, stratosphere, mesosphere, and ionosphere, up to that, the studies, the change in atmospheric conditions were studied. So up to MST, mesosphere, stratosphere, and troposphere, the radar, wind profiler radar is used, beyond which lidars are used. Lidars are used to study the ionospheric studies. So that they work with 53 megahertz, and say it radiates various pulse widths from up to 16 microsecond, and with various say pulse repetition frequency, and it does a pulse integration, as I said earlier, and it has a pencil beam of 2 degree in zenith, and they swings in 4 direction to get the zonal wind and meridional wind, and this round the clock they do to study the atmosphere. And coming to one more application where this phased arrays are used in space application is in satellites. In satellites, we call it as the satellites which does the observation on Earth. We call it as a remote sensing satellite. So normally, how a remote sensing satellite works: once a satellite is put into an orbit, the satellite has an payload. Earlier, it was an optical payload. So that optical payload has it will be seeing the earth. And what happens is this all these earth, the layer of earth, will get the lights from the sun. The sunlight hits the earth and it gets reflected back, and this is more or less like a camera, optical camera, which captures that images, and with that it studies. So to do that, so this particular satellite should always be in a particular orientation when it sees a particular place. For example, if this particular land, if it wants to see this, the angle between the sun, particular land, and the satellite, this angle should always be same when it is seeing this particular place. That is what we call it as a sun synchronous orbit. So because with same illumination we should take a photograph regularly, then only those can be, the informations will be same, and the changes in information from the earlier to now can be easily brought out. So if you take at two different illumination, the information is totally different, and we cannot do any comparison to do the forecasting or other things. So that is one trickier thing in say optical satellites which are doing remote sensing. All these optical satellites will be put in a sun synchronous polar orbit, SSPO. We call it as SSPO. But the basic thing here is it is only a passive receiver, an optical receiver, optical camera in it, that tries to take a photograph of a land which is lit by the sun. But this camera, once after receiving it, it has a variable filters like IR filters, infrared filters, thermal filters. So with the different filters, different informations can be taken. For example, if they want to see a land and vegetation growth, they use a different filters. If they want to see the ocean area, the ocean reflections are always blue, they use a different filters. So likewise, once the thing is taken, once the image is taken through a particular filter, that gives a different information based on your requirement. So this we call it as a passive sensor because the source is from the sun. But the next thing is like using phased array, we go for an active sensor like radar. We radiate the ground with our own signal, RF signal. That RF signal hits the ground and comes back, and we take that particular signal and we try to make an image out of it. So that is called as active sensors. So this active sensor now doesn't depend on sun, so that doesn't require any sun's illumination. So what it can do is it can radiate the signal towards the ground, and it takes its own echo like radar, and with that echo it tries to map. So since it is doing, it has got a lot of advantages. See what happens is here in passive sensor, since it is dependent on the sun's illumination, suppose if there is any cloud in between, or in that case if there is a huge cloud mass and raining, then there will not be any picture. The picture is only will be cloudy. But whereas here the satellite is dependent on its own RF energy. It can take the images even during night, or even when the cloud is there, this RF strong signal can pass through the cloud and take the images of the ground or terrain. So this active sensor, especially we call it as a radar based satellite, or synthetic aperture radar we call it as. The synthetic aperture radar has a very wide advantages than a normal remote sensing satellites. So how a synthetic aperture radar works? A synthetic aperture radar creates a two-dimensional or a three-dimensional reconstruction of an object. For example, here if this is the ground and this is the satellite path, the satellite path will be moving. So what it does is it will be radiating a signal towards the ground, and that signal is received by the antenna. But the moment the signal hits and comes back, the antenna would have moved to another direction, and it's so this transmitted signal again would have come to a new direction, and again it receives. So more or less like it is like when the satellite is moving, the ground path here, the reflection continuously is seen by the radar. So more or less like a very big, such a big antenna is there in the space, which could able to illuminate the entire ground path at a single stretch and take a reflection. Likewise, it is more or less like that. So though we have a small antenna here, since because of its movement and the thing, it is like it could continuously see illuminate the ground, and continuously it can take the reflected echo from the ground. So that is what we call it as synthetic aperture. Like it is no, the real aperture is small, but it's more or less like a higher aperture. It could able to continuously illuminate and take it. And based on the beam width of the array antenna, the swath, how much area it could able to illuminate and take it, we call it as a swath. So that much area of reflection comes from the ground, and when could able to take this reflection and do analysis of it, you could able to reconstruct the image of this particular swath. So it takes a particular swath in one orbit, and this swath in the next orbit, and this swath in the next orbit. When all these things are reconstructed, a complete map of a required area of a big city or a big state can be taken. This swath itself will be in kilometers, like a swath will be a minimum 100 kilometers or 150 kilometers, a minimum will be there, because since the object is, the target is at 600 kilometers, its beam width will be, even if 1 degree beam width will be 60 kilometers, swath will be there, 60 to 70 kilometers swath will be there. So this is how radar images ground. So by moving on it, earlier the synthetic aperture was radar was used using a plane. It was fixed on a plane, and the plane was moving, and it was taking images. Then what happened was that particular technology now is being fitted to the satellite. Now satellite is from the orbit, does the same thing, and it takes the images of the of the ground. So compared to that, the synthetic aperture radar has got a huge advantage compared to the optical imaging satellite. Like it can even captures images by its own radiation, microwave radiation, and even it can take during all weather conditions, when it is cloud, smoke, or darkness. And here what happens is, like here, since it is optical, the bandwidth is only limited. Like you can go only to the visible spectrum. In that visible spectrum, slightly infrared and or else short wavelength nearer to that can only be imaged. But here, since it is RF spectrum, complete RF spectrum can be used. Each and every say terrain or application, a different RF signal can be used. So based on that, it has got a wide bandwidth, so that a huge information, a finer information can be got through a SAR compared to an optical imaging satellite. And compared to this is a same place taken by an optical sensing satellite. With that area, particular area covered by a cloud, you could see only a cloud which in the photograph. But whereas the right side, even seeing through the cloud, the landmass has been taken photographed through a C-band synthetic aperture radar. So this is the main advantage of having a synthetic aperture radar as a satellite. And as I told you, one of our the first synthetic aperture radar what we could able to send was a radar imaging satellite, RISAT. We call it as that. RISAT is a C-band synthetic aperture radar which operates in 5.35 gigahertz, and the C-band, the wavelength being smaller, this had a very good say application towards like agriculture and called crop cultivation. Like if you see, even when the paddy fields are done, see this is the spectrum what we could able to see when the crop is being grown. If you could able to see using a visible IR spectrum, it could able to see only the top layer of the once it is greenish, the top layer of the growth it could able to see. But whereas by using IR spectrum, a slightly lower could able to see. But whereas by using the say synthetic aperture radar in a higher thing, you could able to see even the say up to the bottom of the depth of the thing, like whether the soil is even moisturized or not. Up to that level, we could able to see by using the radar imaging satellite. Even some radars are so powerful, even if something is submerged into the ground. So say we call it as a ground penetrating radar. Something is buried inside the ground can also be seen by the radar. So such level is the power what a synthetic aperture radar has. And this was our first imaging satellite, and it was very successful. And even series of RISAT 2, 3 has been imaged, and they are giving a round the clock imaging to us. And coming to next thing, recently launched is the NISAR. NISAR is nothing but NASA ISRO jointly developed synthetic aperture radar, launched from Sriharikota in this July. And this is this is the first time in the entire world a dual synthetic aperture radar is being sent through a satellite which is having a single bigger antenna. This is it's itself, this antenna itself is a marvelous. It is a 12-meter antenna. 12-meter antenna. It was stowed inside and kept it, and after that the deploying itself took a lot of trials have been done in the ground. It will unfurl on its own. something like we are closing our umbrella and opening our umbrella during real time during the rainy time. This was fell and kept it during the launch, and after going top, it unfurled on its own to a 12-meter bigger antenna. So this is a single antenna where both synthetic aperture radars, one in L band and one in S band, both the bands operates. So here, being a dual synthetic aperture radar, an L band SAR was designed by NASA, and an S-band SAR was Polric radar was designed by ISRO, and this particular satellite has both of it, and this is a joint version made by both. And the main advantage of this particular thing is it can map the entire Earth, even the icebergs getting depleted up to say a resolution of 5 to 10 meters. Up to 5 to 10 meters, a small iceberg. If there is a small say shift in land, say for example tomorrow, if you would have, for a construction, if you would have dug a hole in your ground, in your house backyard, which is slightly more than 5 meters, the next day if it photographs, it can say that that particular area the land has been removed. So such a level of precise thing this particular radar can give a map, and this is meant to map the entire earth, say 4 to 5 times in a month. So in a month, nearly 4 to 5 times, it gives a complete digital globe of earth. So such a level variation in the say ground level or earth or ice level or oceanic level movement in tropos can also be easily seen. So this is mainly meant for disaster say warning system. If anything is getting a disaster is going to come, it could able to get the earlier information and give us. And also it is also planned that once the initial information is taken, the data will be given to universities for further analysis and so. And towards that, this is been made, and this is the costliest satellite to be ever launched. The cost of this particular satellite is 1.2 billion US dollars. Now this has been launched, it has become operational, and it has started sending images also. Even our own payload, S-band payload from this has taken photographs, and it has given the very finer informations of our Sundarban forest. It was nice, and it is coming up. Hope this will give a lot of useful information to our community. So this is my end of my presentation, and any questions you can please ask me.
Thank you very much, sir. And we
Yeah.
are having two questions from the audience. First one,
Yeah.
which antenna material is preferable for high gain and minimum loss?
Antenna material.
Yes, sir.
Okay, actually, if it is say actually see if it is a say aperture antenna, as I said you, it will be with aluminum material only. But if you are going with say microstrip antenna or conformal antenna, copper is the very good ideal material. But the loss wise is again not only with the material, it is also with the dielectric substrate what you have. The ideal dielectric substrate is air, equivalent to 1. If you have, then it's fine, the losses will be minimum.
And thank you, sir. Second question from Dr. Suvita. And
Yeah.
what bandwidth and data rate limitations challenge real-time radar imaging from space-based phased array?
Okay, radar imaging is not in real time as of now. Radar imaging is like when it is coming up, it takes the image and immediately in the next pass it sends back to the ground station, and from in ground station only images are processed and it's been taken. So it is not in real time. Tracking is in real time and imaging is not in real time basically. Okay. It is near real time. It captures and in the next orbit it sends the data to the ground, and all the processing, the corresponding processing happens in ground.
Thank you, sir.
Yeah.
There is no more question from the audience. No more questions, sir.
Okay. Thank you. Thank you for
Thank you
giving me
very
this
much
opportunity.
for the insightful and clear session, sir. That was very interesting for us also, sir.
Thank you. Thank you, ma. Thank you for giving me this
Thank
opportunity. Thank you.